Okay, good afternoon, everybody. Welcome to the but you can hear me there. It's not working. Okay, now it's working. I think now it's working. Okay. So welcome then to the Institute, or to the Colloquium of the Institute of Physics of the University of Sao Paulo. And today we are very happy and glad to receive the visiting researcher and professor Henrik Rønnow from the École Polytechnique Fédérale of Lausanne. And before starting with his talk, I would like just to introduce very briefly about the trajectory of Professor Rønnow. He's a Danish-Swiss scientist. Actually, he got his undergraduate in two different careers of physics and math in 1995. Then in 2000, he got his PhD diploma in University of Copenhagen. And after that, he moved to do several postdocs in University of Princeton, Chicago, and also back to Europe in working as a scientist in Grenoble, London, and after a permanent scientist also in ETH in Zurich. But finally, he moved to Lausanne, where he went to get the position of assistant professor, first in the University of the École Polytechnique Fédérale of Lausanne. This is the French part of ETH, of course, in Switzerland. And where he also founded the Laboratory for Quantum Magnetism. And from then, he just did a lot of, contribution in many kind of aspects. He also participated in governing activities, like he was a member of the EPFL Research Commission, the president of the Swiss Neutron Scattering Society, and chair of the European Neutron Scattering Association. And from then also, he active contribute to many fields in condensed matter physics. In particular, he has a relevant experience in quantum magnetism, strongly correlated electron phenomena with novel electronic properties, high TC superconductors, and skyrmion, and novel quantum materials as well. And in addition, we have to say that he's an experimental-oriented researcher where he has a completely nice contribution in neutron scattering. And this is something that today he will just share with us, his all expertise in neutron scattering. And we would like just to thanks again, Professor Rønnow, to accept this invitation. And please, now the stage is yours.
Thank you very much, Julio, and thanks to all of you for coming. It's really we've been here since last Friday, and it's been a great pleasure to visit. I'm visiting together with my colleague, Ivica Sivkovic, who's also here. And so, what I'll talk to you about today is I chose, rather than making a very overall view of neutron scattering, etc., I wanted to show you some of the details that we do. So it will get a little bit technical, but on the other hand, you will actually get to see the real stuff at the bottom of it and not just the superficial overview. And there will be a quiz in there where I'll ask you to try to guess why I called this material here strontium copper borate a deep purple crystal. It's actually an insulator, and it is actually deep purple, but it has a secondary meaning. Okay? So before we do that, I just want to mention that what I'm going to show you is the result of many years of work in my laboratory, in the laboratories and groups of many collaborators amongst other things. Actually, I'll show you some really beautiful work that was done by Julio when he was actually working in Lausanne, and which we then continued to collaborate on, and which resulted in a very nice publication a couple of years ago. Okay? Nevertheless, let's take a little bit of a step back. And so Julio mentioned that our lab is called the Laboratory for Quantum Magnetism, and I'll try to motivate what we mean by quantum magnetism and why we like to study it, why we like to do neutron scattering, and then I'll tell you about some of the results we have on this particular compound, strontium copper borate. Okay? So Quantum materials or quantum matter, we hear that a lot these days, but what does it really mean? Because at the end of the day, all materials are quantum. Electronic structure is quantum in nature. Electrons are fermions. We fill them into electronic bands, and that determines the electronic orbitals, the chemistry, whether it's a metal or an insulator. The crystal structure has vibrations, which are bosonic quantum particles. Magnetism comes from unfilled shells, and the electronic shells themselves are the result of quantum mechanics. So what's even the point of calling materials quantum if all of them are quantum? The reality is that there are many phenomena. This desk, if I want to describe the sound waves running across this desk or why a piece of metal is conducting, I can actually do that with semi-classical theories where I do not need to invoke quantum mechanics. I can make an effective model that's purely classical in nature. So what we mean when we talk about quantum materials, we mean materials where we actually really either need quantum mechanics to describe why they're doing what they do, or what they do is actually useful for quantum applications. And so just to give you an idea of how large the scope of quantum materials is, if we take just something as simple as permanent magnets, which you will find in any piece of device, your mobile phone, etc. So here in the Julio's group, there's a lot of work on samarium cobalt-5. You can also have neodymium iron boron. And these are materials that have been known for 30 years or more, which are used industrially across the world in hundreds of thousands of tons per year. But actually, we do not have microscopic theories of these because they are metals, but they have strong electron-electron interactions. And if we try to do things like that density functional theory, expensive, but you can go down and you can take something as simple as iron, and you can measure the excitation spectrum of iron. So then you will find that there are excitations. I apologize for the slightly low quality picture here, but this is neutron scattering data as a function of momentum and energy of the excitation spectrum of iron. And what you see here is the simple semi-classical model of iron, which doesn't work. And only in the last 5 years or so have numerical methods actually evolved to a point where we can actually describe with some accuracy the magnetic excitations in simple metallic iron. Okay? So in fact, there's still a lot of work to be done to develop our understanding of how to treat the quantum antibody problem so that we can describe even the simplest technological materials that we have available to us. Okay? Then the other step I mentioned is some materials we need quantum mechanics to describe them, but they can actually be useful for applications where quantum mechanics are relevant. One would be superconductors, lasers, quantum optics. Nowadays there's a lot of focus on 2D materials, graphene, magnetic graphene, Majorana fermions for quantum computing. So that's a realm of quantum materials where it's not just that we need quantum mechanics to describe them, but we actually also want to use them for applications where the application itself is quantum in nature. Okay? If we stay within the realm of fundamental science and fundamental physics, we can use materials and devices made out of materials as little laboratories in which we can reproduce particular models and then study experimentally the behavior of these, so essentially have them as quantum simulators. Here is a former PhD student in my lab who's proposing that one can realize something called the SrCu2, Shastry-Sutherland model, by taking little flakes of graphene and like quantum dots, and then actually effectively have a model which is similar to the model that some theorists like to use to describe basically the surface or the boundary of black holes. So mapping one problem onto another problem, and then rather than trying to look at the universe, trying to look in the lab at little pieces of graphene and study not the same physics, but the same mathematical model. Okay? And that's a little bit the direction we'll go in when we talk about quantum magnetism. It's basically saying that we take materials, not because we're particularly interested in that material itself, not because we think that material will become a great technological application, but because the material it realizes or is representing a many-body quantum model which we don't know how to solve, so we can do experiments on it and learn and help the theorists develop their theoretical approaches to get further into the understanding of the quantum problem, which we can then apply to materials that might have technological interest. And so what is the problem of many-body, the quantum many-body problem? Well, many-body systems are generally complex. Here's a small subgroup of a protein. It has about 1 million atoms. So if I want to describe the structure that is shown in this picture, I would need to specify the x, y, z coordinate of every atom. So I'd need about 3 million numbers to do so. And then in principle, I've specified exactly the structure of this protein. Okay? I could also go to spins, to magnetism. And so I could take spin 1/2, which is a little quantum mechanical particle. Okay, if I only have one spin, it can be pointing up, it can be pointing down, not much is interesting. But if I have 2 of them and I couple them together in such a Hamiltonian, so an energy which is given by the dot product between the 2 spin operators, multiplied with some exchange constant here, and if that's positive, then they would like to point anti-parallel to each other. So classically, any one of these configurations that I'm showing here would be at the lowest energy state. It turns out quantum mechanically that the ground state is this singlet, which is a linear combination, a superposition, an entangled superposition of the up-down minus a down-up state. Okay? I can take 4 of those and write down, so this would be the ground state of 4 such spins. If I took 16 of these spins, then I can diagonalize it on a mobile phone. But if I take 40, 48, 46, 48, something in that order, that's actually the world record of how many spins coupled together in this very simple model that you can diagonalize exactly on a computer. And if you take 40 of them, then the number of, so here you see, so basically here is 1, -1. Here's -2, -2, 1, 1, 1, 1. These are the coefficients in my superposition of quantum mechanical states. And so if I wanted to describe the 40 spins, the ground state is a superposition of many different configurations along the 40 sides. And the number of coefficients I will need in that superposition is 1 million numbers. Okay? And so essentially what it is that classically, we do not have the concept of superposition. A particle is here and only here. It's not sort of in a superposition between being here and being here. So we only need a linear number of numbers in order to describe the system size, whereas in the quantum mechanical case, the number of states available increases exponentially, or as a power law, with the system size. So 2 to the power of n, where n is the number of spins we have in here. Okay? And what we want to describe is a piece of material which has, in a cubic centimeter, there would be 10 to the 23 of these spins all interacting with each other. So we really need, so there's no way we can ever build bigger computers and diagonalize a system with 10 to the 23 spins. So we need either analytical solutions or approximate numerical methods for this. And just to mention, there does exist a few of these. So if I took this and I just couple spins in one linear chain, so in one dimension, then actually there does exist an analytical result. It's even a very old result. It's almost 100 years old. So Hans Bethe in 1931 wrote down a recipe for the exact ground state of that problem. Right? So there are a few of these models which we actually know exact solutions to, but the vast majority not. So for instance, if we do the same in 2 dimensions, then actually we have no exact solution. We have a number of approximate, so perturbative solutions, numerical solutions that all point to, so we think that we know what is happening, namely that it forms such an antiparamagnetic state, but we do not have an exact solution to the problem. And moreover, if we took such a system here and we said that each of these spins is actually an electron or a hole in a copper oxide lattice, and we remove a couple of them, so we remove a couple of these electrons, then actually we get the phenomenon of superconductivity, which researchers have been trying to really get the grasp of for 3 decades, We have approximate numerical evidence of how this functions, but we're very far from having a quantitative theory of the phenomenon. Okay, so this is basically why we like studying spin models, because we can take you could have other quantum many-body problems. You could take a 2D electron gas. You could take a set of nuclei, or you can take the hadrons inside a nuclei and let them interact, etc. But here we can actually take very well controlled in a piece of material, in a solid piece of material. We can choose by choosing which element, copper, nickel, cobalt, which spin number we have. We can make all the fundamental phenomena of quantum mechanics. We can have a superposition between up and down. We can have an expectation value, for instance, of this state here. If alpha is equal to beta, the expectation value of the spin would be 0. So this would be quantum fluctuations. We can make entangled states or quantum correlations, such as this singlet state here, where we can neither say that the spin is up or down, but we know that if one of them is up, then for sure the other one is down. So we have entanglement. Okay? So we can realize all of that. And we can find materials such as this blue crystal. I've mentioned to those that followed the lectures in the last couple of days. Amongst you, who has grown a blue crystal when you went to secondary school chemistry class? No? Okay, Brazilian educational system is different. So around the world, many kids have grown this blue crystal that is actually a one-dimensional chain, the one that has an exact analytical solution given bound in 1931. Okay? But anyway, so you can find materials that will realize different lattices, different interactions. We have theoretical methods, we have experimental tools that can then realize a large number of different phenomena, quantum mechanical phenomena, of which I will show a couple of during this lecture. So essentially, I'm from Denmark, and so is the toy Lego. That at least you know also in Brazil, right? So okay, good. So with Lego, you have little blocks you can put together, and you can make many different things. So essentially, I think of quantum magnetism as an arena, as a playground in which we, with the help of the chemists that can make crystals for us, we can actually have different models and then study with experimental tools and comparing to theoretical methods what is happening in these materials. Okay? So in order to do that, of course, we need experimental tools. And luckily, there's a large number of really useful tools available to study magnetism. We can measure susceptibility. So here's an antiferromagnet. We can see that because as we start to lower the temperature, susceptibility goes up a bit, but then actually it turns over, and then it suddenly drops down an exponential here. So actually I can tell just from this that there's a gap opening in the system. So actually I'm forming such singlets that we mentioned before, which have no net magnetization. I can apply a magnetic field to such a singlet state, and eventually I will break the singlets and produce triplets, which are magnetizable. So I can magnetize the system. So by doing this, I can say, okay, so I have a system which in this case here is a ladder or a chain of such spin pairs. I can do specific heat, which works not just for magnetism, but for any material that exhibits phase transitions, and I can track phase transitions as a function of temperature and magnetic field. I can also use so-called local probes. I can use nuclear magnetic resonance. I can shoot muons, which also carry a spin into the material, or I can use electron spin resonance and locally basically measure the precession frequency of some spin, be it a nuclei, a muon, or an electron, sensing the local magnetic field inside a material. And that will tell me something about what is the local field at different positions inside my material. But there's one technique that is particularly powerful and which really is one of the reasons why this experiment theory interplay works so well in magnetism, and that's neutron scattering. So neutron scattering is fairly simple. You take a neutron, you shoot it into a material, into a sample, with a well-defined incoming wave vector. Now the neutron is a massive particle, so if it has a wave vector, it also has an incoming energy, and then it comes out, and you can measure in which direction, so how many neutrons are scattered into a particular final wave vector and final energy, and whether or not the spin of the neutron was flipped. Okay? So that means that we can transfer between the neutron and the sample, we can transfer momentum, energy, and spin. And when we do that, what we see is basically inside the material, what types of momentum transfer, energy transfer, and spin transfer are possible, and so we can learn something about the order and the dynamics of the sample. Okay? So this looks very convenient. It's a little bit more inconvenient in reality because this source of neutron is not a little yellow dot on a screen. You actually need a large facility such as a nuclear reactor. This one is in Grenoble. The sample, in order to have enough counts, you need to have a large sample. So this is a PhD student who went on to become the director of the main national lab in Switzerland. And that, by the way, is the same blue crystal or similar blue crystal to the one on the previous photo, and he's very happy about that. Then you need a detector, which is not a little thing here. So here's one instrument where you have a 16 square meter detector. So essentially, these are large-scale facilities. There's only a good 10 of them around the world. They're expensive. They cost in the order of $1 billion to build. And they serve a large community who measures not only quantum magnets, they measure biological systems, they measure material science, etc. So these are facilities similar to synchrotrons. You have a synchrotron nearby here. And hopefully one day in not too far future, you will also have a neutron source. And so just briefly about neutron sources. So neutron scattering actually really started as a side activity to research reactors built for reactor physics. Then people started building dedicated facilities just to do neutron scattering. And now there's sort of the recent push which is going on in the past 10, 20 years to build the next generation of such facilities. So there's a spallation neutron source in Oak Ridge in the US. There's a J-Park facility in Japan. And in Europe, we're building in Sweden the European spallation source, which is soon completed, and where Switzerland is quite heavily involved. And actually one of these instruments called Bifrost, which will really be a dramatic improvement over what we can do today, we're directly involved in our group. Okay? And so these are facilities, basically. This is the ESS. This here is a 1 kilometer long proton accelerator. So you can really see they are not quite the size of CERN, but they are big machines. So this one here has a budget of 2 billion euros. Okay? And this here is what I could find on the internet, information about the facility that will soon come to you. And so this will be multi-purpose facility, but one of the things is predicted as guías de neutrons. So that's the neutron guide hall. And that's where the instruments will end up. Okay? So why is neutron scattering so great? Well, actually, because the reason why it's so great is that it's very simple. Neutrons interact very weakly with matter, which means that first-order perturbation theory is valid. And so that means that all that we have to do is to take the interaction between the neutron and the sample, and then take the matrix element between the incoming, the initial state of the sample, the initial state of the neutron, the final state of the sample, and the final state of the neutron. Okay? Now, the neutron I can write down as a plane wave. So an incoming plane wave, an outgoing plane wave. And basically a plane wave, once I have this thing here, basically what I end up with is a Fourier transform. So that means that the fact that I treat the neutrons as plane waves means that up here I just get a Fourier transform of this interaction with the sample. Okay? We also have to have energy conservation. So basically the energy transferred by the neutron has to be equal to the difference between the initial and final energy of the sample. So this is a delta function, but mathematically I can write down this delta function as such an integral, and you will notice that this integral is actually becomes a Fourier transform with respect to time. Okay? So that means that what we measure is a Fourier transform with respect to space and time of the interaction between the neutron and the sample. In the sample we have electrons. These electrons carry a spin, and they carry an orbital angular momentum. And actually, the neutron itself carries a spin, so we have a dipole-dipole interaction. This looks like a little bit of an ugly interaction term, but magic happens, and once I Fourier transform this, it becomes very simple. So what I end up with, the cross-section, which is the intensity I measure in my Newton experiment, has some fundamental prefactors that I know all about. It has a dipole factor, which is very simple to calculate. It has a magnetic form factor, which tells me something about the size of the electron cloud that carries the magnetic moment. And then I have the Fourier transform with respect to space and time of something as simple as a spin-spin correlation function. So basically the correlation function between a spin on one side at one time with a spin at another time at a later time t. Okay? And this quantity, the spin-spin correlation function and the Fourier transform thereof, which we like to call the dynamic structure factor, that's actually, that has encoded into it a lot of the properties of a collective system, because it tells us what is the correlation between different sites at different times. And for instance, if I had inside this system, if I have something oscillating, you are familiar with phonons, right? So which are vibrations of the crystal lattice. If I have a magnetic system, I can have a similar magnetic oscillation that will have a characteristic frequency like as sinus of omega naught t. Once I Fourier transform that with respect to time, I get a delta function in frequency. H bar times frequency is an energy. So when I do an energy scan of Newton scattering, I would see peaks in here corresponding to the frequency at which of the fluctuations in my sample. If I had something that decays exponentially with time, so a damped oscillation, I would get, instead of a sharp delta function peak, I would get a Lorentzian peak with a certain width. Now there's a couple of special cases. If I measure explicitly at zero energy transfer, I can inspect my Fourier transform and see that that actually corresponds to, basically, I need to have something which is independent of time. So I need to have something static, like static order. So if all the spins, all the magnetic moments in my sample order, for instance, into a ferromagnet, then I would get a signal which is the same as the Bragg peaks that you see when you do X-ray diffraction of a crystal structure. I can also, however, integrate over all frequencies, and you can then see what happens is that the integral over frequency becomes a delta function in the two times in the problem. And so that means that the energy integrated structure factor, or the instantaneous structure factor, becomes equal to the equal time correlation function. So that means that even if I do not have a static correlations in my system, they are allowed to fluctuate in time. But what neutron scattering does is it takes a series of snapshots and it analyzes each of these pictures and sees how much correlations there are, and then it takes the average of all of these correlations. So even if things are fluctuating, we can still tell whether on average neighboring spin, for instance, are somewhat correlated or not. Okay, so that's essentially a very, very brief primer to neutron scattering, and it's really the power of neutron scattering is that it is so simple, and it is that this cross section is always exact. We have many other probes of condensed matter. We can measure resistivity. We can do Raman scattering, X-ray spectroscopy. But very rarely do we know all of the prefactors in the interaction between the sample and the signal that we measure. So neutron scattering is expensive. We need the big machines. It's statistically limited. The interaction is so weak that even when we have big crystals, the statistical quality of our data is limited, but we know very accurately what we're measuring. Okay? So now let's take a little bit of a sort of detour and ask, okay, so I said quantum magnetism allows us to investigate what happens in matter. And just to make a parallel, most of you are familiar with the electronic structure of matter and the fact that if you take nearly free electrons like this and you put them into a crystal structure, then you open at the zone boundaries, you open bands, you can fold that back in, and that's how you get a band structure. Okay? Now, then you can very easily understand things about a material. So basically, once you fill in electrons, then if you have an even number of electrons, then you end up with the Fermi energy being in between the gaps here, so then you have an insulator. If you have an odd number of electrons, then the Fermi energy ends up being in the middle of a band, and you have a metal. Okay? So it's super simple and beautiful, and it really works for a very large number of materials, except when you have strong correlations, strong interactions between the electrons. And possibly the simplest example of that is you take a square lattice like this, and you put electrons on the square lattice. And now, if you put exactly one electron for each site, in principle, you now have an odd number of electrons, and according to what I just said before, you should have a metal, right? So basically, you should be able to have a current flowing with just a small electric field applied to the system. However, what happens is that because you have a Coulomb interaction on each side, given by an energy scale U here, if that's large, then actually the electrons will repel each other and they will get stuck. And if I have exactly one electron on each lattice site, it's a little bit like a traffic jam. There's no place to go. So even though in principle the car's on a road, in principle it could drive, they can't get anywhere and everyone is standing still. Okay? So that is known as a Mott insulator, which is a collective state where even though it should be a metal, it's actually an insulator. This happens in reality, and perhaps the most famous example is the family of materials called cuprates, which contain exactly such square lattices of copper and oxygen. And it turns out that indeed, if you have exactly one electron per site, then you have you have an insulator, and this insulator, the spins order in an antiferromagnetic pattern, similar to what I had on one of the earliest slides here. Now, if you remove a couple of electrons, you make a couple of holes in this, now they can start to move around. So you would think naively, okay, fine, so now I will recover a simple metal. It turns out that's not at all the case, because in fact what happens is that you get a superconductor. These are the so-called high-temperature superconductors. You can have superconductivity all the way up to 150, 160 Kelvin. From 150 to 160, you have to ask Julio, because you need to apply approximately 5 GPa of pressure to get there, to get the world record. And not only is it a superconductor, but around you have a strange metal behavior, you have a strange magnetic and charge behavior, and only when you really put in remove a lot of electrons do you recover something that looks similar to a proper simple metal, okay? So this here is really all about trying to understand the quantum many-body problem. And a lot of effort has gone into trying to understand this, both theoretically in simplified versions and experimentally in the many different realizations there are, the many different variations there are of the cuprate lattice. And as I said, we have some ideas about what's happening, but there's still a lot of details that are not understood, and it's a very complicated problem. Okay? Now, as a physicist, in order to understand things, one of the things we like to do is to simplify matter. So we could find a different material, another blue crystal here, which actually also has such square lattices, but where we really have exactly one electron per site, and where the ratio between the Coulomb interaction and the hopping is much higher, so that it really is very well defined, just a quantum magnet. There's no electrons hopping around anywhere. We get an antiferromagnetic ground state, and when we try to make excitations and measure them with neutron scattering, we get simple vibration of this antiferromagnetic lattice. We call them spin waves, and everything is very simple. Essentially, semi-classical theory would be able to describe that. I've spent a great deal of my career explaining why there's a little bit of missing intensity here. That's the only signature of anything interesting happening in this material. Okay? So that's almost too simple. Only primitive people like me will spend their career studying something as simple as that. But you can go a little bit more sophisticated. What you can do is you can take such a square lattice, you put a spin on each side in such a square lattice. But now, in addition to just having couplings along here, we put also some coupling along the diagonals in such a crisscross pattern as this one here. And if this coupling J here is much larger than the coupling J prime, then essentially each of these diagonal bonds will form a singlet. And the ground state of this model, which was invented by two theorists, Shastry and Sutherland, the ground state would simply be a product state of a singlet on each of these bonds here. So fairly well defined and easy to work with ground state. So in fact, this is one of the few models in 2 dimensions that has an exact known ground state, as long as J is much larger than J prime. Okay? And what is really interesting is that there is this material, strontium copper borate, which contains copper, oxygen, and strontium and boron in such a pattern that actually it realizes its topologically equivalent to this square lattice exactly to the Shastry-Sutherland compound. SrCu2 model. Okay, so that means that we can now actually do experiments on this system here and compare with what theorists might be able to calculate. Unfortunately, this is the only material we know that realizes this model. It would be great if we had a few others we had greater variability over, for instance, the ratio between J and J prime, etc. But this is what we have. And because you have this interesting arrangement of these spin pairs, it turns out, for instance, if I take one of these singlets, I create a triplet, and now I want this triplet to be able to jump over. So I've added some energy, and this energy, in principle, I would like that to be able to move from one triplet from one pair to the next, etc. But because of this orthogonal orientation, it basically in lower order of perturbation theory, nothing happens, and you actually have to go to 6th order in perturbation theory before you can have any movement of these excitations. So you get very localized excitations, which is simply a local triplet that sits there. And so if you have something that is local in real space, in reciprocal space, it means that it's independent of momentum. So in other words, you have an excitation with a finite energy, but then that energy is independent of momentum. In band structure, we like to call that a flat band, and there's quite a bit of interest in flat bands, for instance, in twisted bilayer graphene and others. So here is an example. So of course, in twisted bilayer graphene, the band that is flat is a fermionic band, it's electrons. Here, these excitations, these triplet excitations here, they are bosonic. So this is a bosonic flat band, but there's also some interest in studying bosonic flat bands. Now, there's a detail that actually, in addition to the main interaction in the system, there's also a so-called Sierzyńsko-Marie interaction that couples not only the dot product between two spin operators, but we also have a contribution from a term that couples the cross product between two spin operators. And what that does is that actually this what appeared to be a flat band, when we looked at it here, if we zoom in with very high resolution, there is actually a bit of dispersion in here, okay? And now we can apply magnetic field, and we will basically change a little bit how these bands disperse. And there's actually a particular magnetic field where the bands, they cross in such a way that here we actually have a Dirac cone. So again, from graphene and related 2D materials, there's been a lot of interest lately in the last 20 years, or 10, 15 years, about Dirac cones in materials. And so here, again, most of the interest is in fermionic Dirac dispersions. Here's a bosonic Dirac dispersion. But I'm not going to talk more about that, just to mention that you can have bosonic versions of what happens in the fermionic band systems. What I will talk a little bit about is what happens to this triplet excitation. So we said that this is a rather localized excitation. So unlike most, if I make an excitation in this table, I create a sound wave which moves across, right? So it's a dispersive excitation. It has a linear dispersion. That's my sound velocity. This one here mainly just sits there. And now if I apply a temperature, so if I increase the temperature, what I would expect, okay, so I have an excitation sitting at 3 millielectron volt. That corresponds to 36 Kelvin. So I would expect that if I increase the temperature in the order of 36 Kelvin, then I would really completely smear out my system. My beautiful product of singlets ground state would basically become a mess of just fluctuating spins, and I would expect to see just a smeared out spectrum like this one here, if I increase the temperature to around the size of the gap in the system, so 36 Kelvin. Now, the peculiar thing is that it actually happens much earlier. You can see here already at 6 Kelvin, I've reduced dramatically. 7 Kelvin, half of the intensity is gone. 10 Kelvin, it's almost completely smeared out. So it happens much faster than we would expect based on just measuring the size of the gap. And so we made this observation. We looked a little bit more carefully into this. You remember I told you that if I have a very sharp, well-defined oscillation frequency, then in my spectrum I should see a sharp peak. If this oscillation has a finite lifetime, in other words, if I excite a triplet and this triplet has a finite lifetime before it decays back again, then I would expect to see a Lorentzian line shape here, so a broadening. Okay, we see a broadening, that's all fine, but when we look more carefully, actually, we can't fit this with a single decay time. In fact, what we get is we get one decay time, one lifetime, which very quickly decays very fast as we increase temperature, and another one that stays much longer. So somehow it's like there are two separate types of response from the system. Theorists were no use. As I told the class this morning, if you have if you're an experimentalist, you have a phenomenon, and you can't really get any theorists to get interested in helping you figure this out, the best thing you can do is that you can make a crap theory yourself, so ugly that the theorists feel compelled to prove you wrong. Okay? And so this is what we did. We said, okay, fine, so a triplet excitation. Now, if I make a triplet on one bond, then actually this triplet might polarize the next spin over here and polarize. So that means that actually, even though the triplet formally sits on a single of these diagonal bonds, it actually has a little bit of a finite size. Okay? And now we make the hypothesis of saying when we increase the temperature, there will be a very small thermal population, basically a thermally activated population of triplets in the system. So a very low density of these guys, but each of them has a certain size. So now I come with my neutron, I create another triplet, and there's two possibilities. Either the new triplet I created is far away from any of these thermally excited triplets, and if that happens, it has a long lifetime, so it contributes to the sharp peak, or it will overlap with a thermally excited triplet, in which case it will decay fast. Okay? And now I can basically, once I know the size, the radius of this thing here, and I would know the size of the gap for the thermal activation, then I can actually predict what would be the ratio of fast decay to ratio of slow decay. And basically that's this crossover here, so the long lifetime component, as I increase the temperature, goes down, and the short lifetime component goes up. This extremely simple model, I would barely call it a theory because we haven't calculated anything, we just make a hypothesis. That's a line which goes through our data points. We can apply a magnetic field, split the triplet so that one side of the triplet goes down to lower end, so we change the gap. And if you change the gap, then the temperature dependence changes, and it again agrees with experiment. Okay, so it's not actually a theory; it's just a hypothesis, but it happens to describe the data. So I'm hoping that theorists will eventually actually catch up and either prove that there's a completely different reason which accidentally gives the same curves, or that actually our argument is a good one. Okay. So that was what happens to this system if you just increase temperature. Now, one could also hope to be able to change the ratio of the two couplings in the system. And in fact, there's a sort of a theoretical prediction that if you change this ratio, you could also add some interaction between these two-dimensional layers. Then you would have a phase diagram roughly like this one here, where if you just increase coupling between the layers, you might actually be able to induce antiferromagnetic ordering, similar to if you had no diagonal coupling at all. But if you were able to increase this J prime, you might actually get to an interesting intermediate state here. And if we look at the couplings that we have in strontium copper borate, it looks like we're actually really close to this new quantum mechanical phase here that people had predicted. Actually, there were about 5 or 8 different predictions for what really happens here, but everyone agreed that something is happening. And one of the things you can do with, if you want to change, you have a material, as I mentioned, we were not able to find another material that has the same model. In fact, this particular material, it doesn't even want to be chemically doped. Anything you try, you put calcium instead of strontium, it doesn't work. So basically, you can't do much. But one really beautiful tool we have available for condensed matter systems is pressure, applying pressure, which changes the crystal structure, and that will change the ratio of couplings in the system. The only thing is that it's really hard to predict how it changes. So it could be we're going this way, this way, and only if it goes this way, when we apply pressure, would we be lucky enough to get some new physics. So we started doing that. We applied pressure, and what we saw was that as we increased pressure, the energy of this gap to the triplet excitation goes down. That's great news, because generally when you have a phase transition between one state and another state, if it's a second order phase transition, you actually expect the characteristic excitation to soften, to go to zero, and then you get the new phase when that excitation reaches zero. So this is good news. It goes down. We managed to get it down to about 2 millivolt from 3, so we need another 2 to get it all the way down to the quantum phase transition. So that was done with one pressure cell. We found someone who had a bigger pressure cell. Now we need pressure cells that can have a big enough sample that we can do neutron scattering, get the neutrons in and out, etc. So here's a Mach 1 cell, which is very complicated to operate. Took a long time to get this experiment to work. We managed to go from 16 kilobar all the way up to 21 kilobar, and we're really looking forward to seeing the gap going even further down. We had even made, I don't know if I included that in the figure, we'd even made some very optimistic predictions that this actually would accelerate and go faster at some point. Then we did the experiment, and basically from 16 kilobar to 21 kilobar, the peak did not move at all. It was very disappointing. It was also very puzzling, because we keep applying pressure, so why is the ratio between J prime and J not changing anymore? So that was a little bit disappointing, until when we looked more closely in the data, we saw that, okay, fine, this peak here is in the same place, but there's something new, and if we track that down, essentially, in addition to this peak just below 2 electron volt, there was now a new peak appearing down around 1 milli-electron volt, which was not there before. Okay? And so, being a little bit brave, we said, okay, well, you know, there's a new excitation. If there's a new excitation, maybe that's because we have new ground state. And so maybe what we have is actually that we went from this singlet product state over here into a new ground state, a plaquette product state over here, and it's just coincidental that in this new phase that has a set of excitations, it just so happens that one of the excitations in the new state has the same energy, and by the way, also the same intensity as this excitation, as the triplet excitation in the previous phase. And then this new one here should be proof that we're in a new state. Okay? So we actually managed to convince a whole bunch of referees and editors based on this evidence that we had actually realized for the first time this new phase here, which is actually also a singlet product state, but now each of the singlets live not on 2 spins, but they actually live on 4 spins. So a 4-spin plaquette singlet state, and everyone was very excited because quite a number of theorists had expected this, which probably helped us in convincing people that we had gone there. It also, in this work, we also found out that if you apply too much pressure, then you actually break the nice symmetry of the crystal. You get into a monoclinic phase, and you get an antiferromagnetic ordered state, which is less interesting from a sort of a quantum many-body perspective. Okay? And now actually we have been working a lot on getting better pressure cells, better neutron spectrometers. The neutron spectrometer that I mentioned that we're building in Sweden is, if you want, is designed to be able to do a better experiment here. It will do a few other experiments as well. But we're not there yet, so how else can we prove that we really are in a new state? Well, one of the techniques, oh sorry, yeah, let's just skip this slide. One of the techniques that is really good for proving whether or not you have a phase transition is specific heat. Right? And this was around the time when Julio joined our lab, and so I told Julio, well, why don't you try to do specific heat under pressure? There are very few people in the world who really do specific heat under pressure, and the good reason for that, it's super hard. Okay, but Julio worked at it, and he actually succeeded. So basically, you take your crystal, you apply a heater, you apply a thermometer, and you work a long time to get this actually to work. And then you get data like this. And I think before this, there had been publications in different materials with specific heat measured under pressure. There had never been any type of measurements that showed this. So basically, at zero pressure, specific heat is fairly boring. It's this broad bump, which is essentially represent the thermal activation up to the triplet excitation. Okay, fine, you know, nothing interesting there. But then basically, once we applied pressure, once Julio applied pressure, This peak moves down to lower energy. Okay, that's fine. The gap is coming down in temperature, so it's natural that the peak also moves down. But it becomes sharper. It becomes super sharp down here. And then actually a new peak develops down here. So it's not directly related to the fact that we saw two excitations in the experiment, but there's this very unusual thing that basically it comes down, becomes super sharp, then the new peak appears, and then the main peak actually broadens out again afterwards. So spectacular data, but actually a little bit difficult to understand, in particular since what the naive expectation would have been that would have soft mode transition that comes back up like this. That would have been the normal expectation for a quantum phase transition. Okay, so we looked at this a lot, and actually it was together with my theory colleague Fredrik Mila that we figured out what is really happening. And actually the answer is here. Right? So it's basically, it's just the same as water. You take water at ambient pressure, you heat it up to 100 degrees, it evaporates into vapor. Okay? You apply a pressure of 100 bar, you have to heat it up to 300 degrees before it vaporizes. If you heat it up, if you apply a pressure of 200 and something bar and you heat it up, then actually you go from having the liquid phase to having vapor phase without ever having a phase transition. And basically this phase transition here has a critical endpoint happening here, and so you can go from water to vapor without ever crossing a phase transition. But if you look at the specific heat at this critical endpoint and around this critical endpoint, you have a huge enhancement of specific heat. Right? And this enhancement in specific heat here is basically exactly the same as this enhancement that Julio discovered in something called borate. So basically what we have is a quantum magnetic analog of the critical endpoint of water, where we go from the dimer phase into this plaquette phase, and if we go up in temperature, we can go around this temperature and pressure, we can go around it without ever crossing a phase transition. If we go down to lower temperatures, like this, then we cross the phase boundary, then we cross the phase boundary here, and then we see the critical line. Okay? So that means we actually understand, and these experiments with specific heat was really the proof that we are in a new phase of this material. Okay? And so here comes the answer as to why I said it's a deep purple crystal. I don't know how well you know your 80s music, but Smoke on the Water was actually recorded at Lac Le Mans, which is where EPFL is, and it was recorded because the concert hall burned down, and so basically you went from the liquid phase to the vapor phase without really seeing any clear boundary between the two. Okay? Now, so that was a phase diagram as a function of temperature and pressure. We can also apply magnetic field to this, and what happens is that we have to apply a large magnetic field because the 3 millivolt, in order to close the gap with a magnetic field, we have to go all the way up to 20, 30 Tesla. And there's been beautiful predictions and even some work using NMR, which I mentioned in the introduction, that up here you can get basically, you can create such bound states of excitations which form a 1/8 ordered crystal, so basically like a Wigner crystal of triplets, if you want. But magnetization increases already a little bit before. And so we looked into that, and basically what happens is that you have as you apply magnetic field, you have the triplet excitation coming down, and you would expect that to hit the ground state here, and then you would have to have a Bose condensation of triplets into the ground state. But you can also have two triplets. If they go close together, they can form a bound state. So now I have a 2-triplet state with a spin 2. And so that the magnetic field will decrease the energy of that one twice as fast. And now it becomes a bit difficult to see, amongst other, because of this Church-Marie interaction, which ones of these actually hit zero first. So which ones are condensing? Are we creating a Bose condensate of triplets or of 2-triplet bound states? And you can do simple model calculations and see that the various excitations you have in such a system will depend on which of these two scenarios are happening. I do realize I'm running out of time. If you don't mind, I will just spend a few more minutes. So again, Fredrik Mila and my theory colleague and his PhD student, they applied a new mathematical tool, tensor network, which actually allows to calculate such things. So they predicted, and according to their calculation, they think that it should be the 2-triplet bound state that condenses. We were able to do the neutron scattering experiments all the way up to 26 Tesla. So this is the only experiment on copper 2 on spin half that has been performed for inelastic neutron scattering up to 26 Tesla. And what we see is that we split the energy of this triplet, and we reach down here around about 20 Tesla, and then we can see what happens to the spectral weight. We compare that to the theoretical calculation. Now I have to see what is what. This is experiment. This is a theoretical calculation. Again, it's not our neutron scattering data are again statistically limited. We have to look at it carefully and be careful not to make a too stringent claim. So, but our data are most consistent with what theory also predict, namely that what the state that is arriving is actually a Bose condensation of 2 triplet bound states. So this is a bit similar to the fermionic case. You have a metal with fermions. You can form Bose pairs of fermions, and now you can condense them into a superconductor. Okay? So this is the bosonic version of that. You have bosonic triplet excitations. You form bound state of them, and then you condense that into a ground state. Okay? So now I'd love to show by measuring the intensity of these as a function of momentum to demonstrate which of these kind of excitations we have. But unfortunately, in that experiment at 26 Tesla, the range of Q that we could access was this big, and we would have needed to access ranges this big to be able to see the predicted variation. And so at 26 Tesla up in this high state, this will take quite a while. Currently, we do not have any instrument, any magnet going high enough in field to do that. But earlier this week, these two gentlemen were sitting in at one of these Neutron facilities, one in Grenoble, and you might notice here on the screen behind them, there's some data. If we zoom in on that, you can see that looks very much like a triplet excitation and some intensity maps here. And in fact, if we go one slide further, so here is this is now at 0 pressure, okay? But at 0 pressure, this is the momentum intensity, momentum distribution of intensity, so the structure factor of the single triplet excitation. This is a prediction from tensor network calculations. This is the 2 triplet bound state, and this is the calculations from tensor network. And you can see it starts to look rather promising, so we're quite excited about this. But the data were taken this week, so I cannot tell you anything about how well it matches or not. You'll have to wait a little bit before we have analyzed and we'll be able to publish this. But we're not sitting still. Actually, you will see that the day before yesterday, we put something on the archive, which is actually about this very high pressure antiferromagnetic phase. And with that, I promise I will stop. So I've told you about the dimer phase. I've told you about the plaquette phase that we found. Now, if you go all the way up here and you actually turn the crystal from a tetragonal to a monoclinic crystal structure, you actually create long-range antiferromagnetic ordering. So to some extent, it's more boring. But if you can do it, then why not? So here's neutron scattering spectroscopy from a spin half system at 5.5 GPa. And the intensity shows that we have rather simple, well-behaved dispersive spin wave excitations, and Ellen, my postdoc, has been able to fit that. And so, actually, to be very honest, there's nothing particularly quantum about this. It's basically we've taken this extreme quantum system, we've squeezed it into a semi-classical antiferromagnet with rather standard and well-behaved antiferromagnetic spin waves. Okay, so with that, I apologize for going slightly over time. But in summary, I hope I've been able to convince you that this material, strontium copper borate, contain a multitude of quantum phenomena that we can investigate with a combination of neutron scattering and bulk probes such as specific heat measurements. And we can realize bosonic excitations and compare them to the fermionic counterparts. We can have a Mott phase of bosons. We can have boson density phases. We can have the equivalent, boson equivalent of Cooper pairs, and we can even condense these Cooper pairs into into a ground state of bound state condensate. Okay, so with that, thank you very much for the attention.
Okay, now we are open for questions. But before, I think I would like just to thank Professor Henrik Rønnow for a nice talk and also for his time during this week, because he also, I didn't mention, but he has also came here to give a mini course in his expertise in our post-graduation. And a part of he's very busy, you know, as a director of the Institute of Physics, what they call Polytechnique Fédérale de Lausanne. He accepted this invitation, and actually the student likes a lot, together with Ibiska, that was giving a very nice course. Okay, now we are open for questions, please.
Hey, thank you very much for the talk, very interesting. So I have actually two questions that are related. So the first one is, what's the order of this critical point that you are showing on the strontium copper boride? Is first order transition, second order transition?
Yeah, so
in the heat capacity.
Oops.
And the second question is basically like, what's the order parameter that is varying over this critical point? And that also I did not catch very well.
Okay, so so basically this is a first order transition. Okay, so now, okay, so we have to remember that this axis is pressure. And so if I did this exactly at 0 temperature, then I would call it a quantum phase transition. Right? So, and we have to be a little bit careful about applying what we know from thermal phase transitions to quantum phase transitions. Some things are similar, some things are different. But it's essentially a first order phase transition in the sense that there are quantities. For instance, I could calculate the dimer correlation function. And the dimer correlation function will make a jump as I go across here. So a discrete jump, and that is the characteristic feature of a first order phase transition, is that you have some kind of order parameter which makes a discrete jump as you cross the transition. Whereas if I were to cross up here at higher temperature, there's no such discrete jump. It's just a continuous evolution. In the case of water, it's the density. Of course, the water is a liquid. There's no structure, but the quantity that jumps as you go across here is the density. So if I go across here, there's a discrete jump in density. When I go across here, it's just a continuous evolution of the density of the material.
So in the case of this material, the correlation function of the dimers is your order parameter?
Yeah.
Thank you.
Okay, another question?
Thank you very much for a nice talk. I have a question about the critical point or the analogy with water. I understand that it's super difficult to make further experiments around that point, but out of curiosity, intuition, do you expect that this analogy with the critical point of water of strontium copper boride will extend to other kind of properties respect to a supercritical state of a fluid?
Yes. So I mean, some of the properties of a supercritical fluid are related to compressibility, etc. So there's a number of observables which are different. You also have the phenomenon of different, while you have no phase transitions, you have lines, so you have the Vidam line, etc. And so you can look for, so for instance, here, so here there's a discrete jump, but here there's still a fairly well, if I look at specific heat, there's a fairly well-defined line here. If I looked at a different observable in water, you would actually have other lines that actually sit in different places. Okay, in water they're actually really close. But in principle, you would actually get different lines going different directions here, depending on which observable you look at. And so now in the experiment, as you say, we have not been able to do that. But we actually do have, so in this paper, we work together with Frédéric Mila and Philippe Corbeau and some of their collaborators. So also here we're applying tensor network calculations. And so they have been able to calculate. So actually they could also reproduce this critical point in the Shastry-Sutherland model. They are not able to calculate so far down that they see this transition, which, by the way, I didn't have time to mention what is, so I hope one of you will ask what it is. But they can now they can actually, in their calculations, they can do exactly this. They can measure or calculate the evolution of the dimer order parameter. They can calculate the evolution of the specific heat, etc. By the way, the specific heat we did measure, right? So essentially, if you want, so we do not see the critical line itself. And one of the reasons we do not see it is because actually the direction in which Julio is scanning is like this. So we never scan across at fixed temperature, scan the pressure. Right? So we never, and since in water, the phase boundary has a slope, so regardless of whether you scan temperature at fixed pressure or pressure at fixed temperature, you cross the phase boundary. Here, you would have to have fixed temperature and scan pressure. That's really hard. But actually this, if you want, are exactly such lines, and so you can relate that to some of the thermodynamic lines. So in that respect, the analogy goes a bit further. Not specifically with water, but with the fact of a critical endpoint of a phase transition.
Thank you.
Okay. Another question. Henrik?
So thanks for this really nice talk. So I was interested in your last results. So you are these last results you are at zero pressure.
At
zero pressure, yes.
These ones.
Yeah, exactly. So is this? So you telling me those are results for zero pressure, and these are tensor network calculations, and then you show spin wave calculations. You say both can describe the data.
Okay. No. So I went really fast here towards the end. I apologize for that. So there's two different experiments. Okay. So this experiment is a zero pressure experiment. Performed on a type of neutron spectrometer called a time of flight spectrometer, which allow us to measure very large regions in residual space as a function of momentum. So these are two directions in momentum space. And that's how we can measure the intensity or the structure factor of these excitations over a wide range. And this is done at zero pressure, so the sample is just sitting there in helium exchange gas. We can have big crystals, so we have a good signal, low background. Okay? So that is what this is. Now, I then jumped to this experiment here, which you see high pressure. And in fact, these are experiments performed at 5.5 gigapascal. So this is actually using an anvil cell. It's not a diamond anvil cell because we need big samples. So it's something called a Paris anvil cell, where we have tungsten carbide anvils, and the sample is in the order of tens of maybe 20, 30 cubic millimeters. So it's not no, hang on, no, I'm wrong. Perhaps rather 8 to 12 cubic millimeter sample, and then we can reach here. But again, to be able to measure excitations from there is not so easy, and we do not get as beautiful data as the one showed here, where as these ones here. In fact, this is now doing a different type of instrument called a triple axis spectrometer, where we really move. We have an incoming beam, we have an outgoing beam defined with analyzer crystals and a single detector, so that we have enough intensity and low enough background. And so every pixel in here is actually moving physically, the analyzer and detector, then counting for 10, 20 minutes, then moving again, counting for another 10, 20 minutes, building up this color map here.
Okay, thanks. So, can you extrapolate and find the sweet spot to find all phases between 0 and 5.5 gigapascal? Because in principle, you have both values of J prime. So in principle, you could be able to find to at least to guess the pressure, to guess the plaquette phase and the other phases in this compound in between both those two phases.
Sorry, I couldn't.
No, I'm sorry. So in principle, I'm just asking if you could guess the pressure, because I mean you have the values of J prime for zero pressure and 5.5, right? So can you guess the value of pressure you'd need to go to, let's say, to the plaquette phase, precise inside the plaquette phase?
We have a quite good idea. Basically, okay, this is not super precise, but it's essentially it's essentially that. So you need 1.8 gigapascal to make the transition between the diamond and the plaquette phase.
Okay.
You need 4 gigapascal to go into the monoclinic phase. Now you will see here unconfirmed, and in fact, later than Julio's specific heat experiments, there's been a Chinese group who has done similar measurements. They were able to go to slightly higher pressures than Julio did back in his days, but they could not apply magnetic field. We could, so there's complementarity between the two. And they report, so actually these black dots, so these dots here, that's Julio's measurement, the large circles are Julio's measurements, and these black dots, they come from this Chinese study, and they say that there's a new phase here, and a good guess for this phase would be that actually while we're still in the Shastry-Sutherland model, so while we still have the square lattice tetragonal crystal structure symmetry, we actually do get an antiferromagnetically ordered state, so that this would be an antiferromagnet, but that has not been confirmed. Right? So all we know is that there's some phase here, and we have not been able to confirm what it is. And we have also tried to measure the excitations here. Those experiments have not been successful. And so to some extent here, we have a very well-defined, so actually you can see we have already all of this stuff happens down below 10 Kelvin. Once we break the symmetry, we actually get antiferromagnetic order at 120 Kelvin, and the J over J prime that we extract, so here, down here we have 0.6, 0.7, 0.8, and J prime over J. When we fit the spin waves here, we get 1.8. So this change in crystal symmetry probably really changes the arrangement of the electronic orbitals and completely changes the magnetic interactions in the system. So it's really a very different system over here.
Thank you very much.
Well, we still have time for questions. No? Okay, I have maybe one question. It's related for something that you mentioned, and it's also something that I already hear in many kind of events and talks. Why strontium copper is the only compound so far as an example of this Shastry-Sutherland? Yeah.
Yeah, that is a good question, and there's no fundamental reason, and probably you could find other materials. But you need a lattice where, basically you need a lattice which is topologically equivalent. So notice here, sorry, I need to go all the way back to the start. You can see that actually in this material, the copper are not actually sitting in a nice square array, but they sit in a manner that, so basically my J prime coupling, which here makes a square lattice, that is actually going sort of in a zigzag pattern like this and like this. And my J coupling here is much shorter. Here it's longer but stronger. And so all you need is a crystal structure which is topologically equivalent, where the couplings are topologically equivalent. And I have been looking through crystal structure databases trying to find, we've even tried to synthesize a couple of them, but we have not been successful so far. There exists some rare earth borates, which does have this crystal structure, but the rare earth iron has a larger moment, and it carries, and basically it then gets a crystal field, which actually means that it becomes anisotropic. And a lot of these delicate quantum mechanical many-body quantum properties requires a continuous symmetry, so the so-called Heisenberg model. If we go back to one of the Hamiltonians I showed, So here I have the dot product between the two moments, And so this dot product is completely independent of it's isotropic. It doesn't matter what my quantization axis is. I could also have written here as Z times sz, so take only the Z component of the spin operators. That would be the Ising in the Ising model. And actually, so there's other interesting things about the Ising model, but all the physics that I mentioned here will disappear. The Ising model does not have this interesting phase diagram. Or it could have Sx times Xs plus Sy times Sy. That would be the XY model, which can also be interesting in other contexts, but it would not have this behavior here. And so we need to search more. I have to admit that when I was looking for it, I was looking through crystal databases by hand. Now there's a lot of DFT people out there who say that they can find anything with machine learning and databases and so on. So one of the challenges to them would be to say, okay, I have a very well-defined problem. I want to have spin half on such a lattice. Please give me one. So I hope that one can convince them, or actually that we try to do ourselves, do a database searches and find another example.
Right. Okay. So any other question? Well, if not, let's thanks again the speaker. Thank you. Thank you also for your presence. Bye.